Hi there, I just wanted to do one more quick video on sort of the basics of interacting with orbital mechanics. Specifically, what do maneuvers do? So we've got the spaceship here. It's the same spaceship I was using previously. We're sitting here in orbit of Kerbin. We're starting in this, what is it, a 100-kilometer equatorial orbit, pretty close to a circle. So when we're doing maneuvers, there's 6 directions that we normally consider doing burns in. That's what we do in order to do any sort of change in orbit in space, is we have to execute a burn with our engines. And I'm actually going to start off by staging this thing a couple of times. So we burn our engine. The engine is going to send out hot gas in one direction. That's going to push the rocket in the other direction. Newton's law. And there are 6 directions we can go in. The first option is we're going to go prograde. And conveniently, when you're doing manual piloting, if you have sort of a maximum level Kerbal pilot, or you have a maximum quality probe core on your spaceship, that's what's going on here. This has a top quality probe core. Specifically, the probe core is this Probodyne Octo 2 is a top quality probe core. It gives us the option to do all 6 things. So we have prograde. That's we're going to burn in the same direction as our orbit. And if we burn in the same direction as the orbit, what's going to happen? Let's actually go ahead and do that. So we're set prograde. That's going to force the rocket to point in the appropriate direction. Then we're going to go ahead and go full throttle. And you can see that what happens is we started in a circular orbit, so the periapsis is moving towards our spaceship, and the apoapsis is ending up on the other side. So as we go to burn forward, what that does is it's going to increase our apoapsis on the opposite side of the planet that we're orbiting. So I'll stop the burn there. Now if we flip around and point the other direction, our spaceship is going to be pointing retrograde. And if we burn retrograde, that is the opposite of prograde, it's going to lower the orbit on the other side of the planet. Note that neither burning prograde nor retrograde actually changes the height of the orbit where the spaceship is burning. They both impact what's going on the other side of the orbit. So we push the other side of the orbit further away or closer in. The next 2 possibilities are we can burn normal and anti-normal. And those are burning up and down. So normal is burning up. If we're thinking North Pole is up, I guess you might want to say north. But burning normal means burning up. And burning normal or anti-normal, the effect that that's going to have on the orbit is it's going to change the inclination. So let's go ahead and give that a try. I'm going to burn normal. And it takes a little while. It takes an awful lot of delta V in order to generate a difference in inclination. It's one of the most expensive maneuvers. But you can see the effect here. If we burn normal, so we're burning straight up, what that's going to do is it's going to tilt our orbit. So the side of the orbit in front of us is going to be higher. It's going to be more north. And the side of the orbit on the other side is going to be lower. It's going to be further south. If we burn anti-normal, it's going to tip our orbital plane in the other direction. Now, the axis that we're tipping the orbital plane around is the axis that we get for an imaginary line from our spacecraft through the thing that we're orbiting around, and then through the center of the thing that we're orbiting around. Now, another thing that's relevant for these inclination burns is that if we're trying to hit another body, when we go ahead and select it, we end up with these 2 points. We have a descending node and an ascending node. Those are on, normally we talk about those as being sort of compared to an equatorial orbit. They're parameters in our Keplerian orbit. But we also have a descending node and an ascending node compared to the plane of another body. So you can see here that we are 17.6 degrees off from the moon. But if we go ahead and select minimus, which is not in an equatorial orbit, the moon is in an equatorial orbit, the minimus is a little bit offset. If we go ahead and set that as our target, we no longer have a 17.6 degree offset, we have an 11.6 degree offset. So we're actually a little bit closer to the plane that minimus is in. Now if we want to match planes with a target, we can do that. And to do that, we want to have a maneuver at the ascending or descending node, either way, with the target that we're trying to match. And then we burn until we get that spin around. And if we get our ascending and descending node to be sort of perpendicular to where they were before, they're also going to be pretty close to 0. So to do this maneuver, we would warp to the maneuver. Then that was a burn radial, I believe. We'll wait till we're done warping. Sorry, not radial, normal. Takes a second to warp, but I do want to demonstrate this. So we're going to burn normal, I think. Yeah, the blue thing is the direction of the maneuver node. So then it's going to be an 8-second burn. So we want to be relatively on target for this. So we want to start burning at 4 and burn for 8 seconds. 10, 9, 8, 7, 4, burn. Then we just burn down until we get to 0. If we wanted to be completely accurate, we would, oh, we're stopping now. So we were slightly off here. You saw that the blue target moved away. But as the result of that burn, if I get rid of this, we now have a 0.5 degree difference between our orbital plane and the orbital plane of minimus. We've approximately matched target, and now we can do a maneuver that would try to intercept it. If we're not in the orbital plane of a target, it's not useful to try to burn to intercept it. So that was prograde and retrograde, change the height of your orbit, height of half your orbit. If you want to circularize a higher or lower orbit, that's going to take 2 burns. You have to burn to raise the other side of your orbit, and then go around to that side, and then burn to change the first side of your orbit. We have normal and anti-normal, which change your inclination. And almost all the maneuvers that there's any reason to do are prograde or retrograde, or normal or anti-normal. Changing your height and your inclination is most of what you want to do. But the last 2 options are radial in and radial out. So radial in, we're going to... radial out, we're pointing directly away from... we're pointing sort of perpendicular to our orbit away from the planet. Radial in, we're pointing perpendicular to our orbit towards the planet. Let's go ahead and burn radial in here. And we have a slightly eccentric orbit, and we're not at any sort of magical point. We're not at the apoapsis or the ascending or descending nodes, or just sort of arbitrarily, but we're going to go ahead and burn radial in. And when we do that, you can see that what it's doing is it's sort of rotating the orbit around where we are. Let's go ahead and flip around radial out and burn the other direction. It's going to do the opposite. So it's sort of changing the center of the orbit. It's not really it's not changing the size of the ellipse. It's sort of changing the position. It's definitely not changing the inclination. And this is sort of an inefficient thing to do overall. We could generate the same effect by doing burns at, by doing either prograde or retrograde burns, either at apoapsis or periapsis, until we had adjusted our orbit to where we want it. But these radial in and radial out are the other 2 directions that we have. There are 6 directions we can burn in because we're in 3-dimensional space. And those are we can also burn in any combination of them. We can burn in any 3-dimensional vector. but any combination of them is going to be a combination of these effects that we've seen for these options. So that's what burning in orbit does, and that's the tool that you have to cause the spacecraft to go places. Going places is just putting it in a different orbit and then waiting for it to orbit around to wherever it's going. Alright, good luck with the assignment, and have fun.